Alright, so this is lecture 7 on the completeness axiom for the real numbers. And so roughly the completeness of the real numbers describes their adherence to one another, or you could think of it as the idea that when we draw the number line, there are no holes, alright? But this is just sort of an intuition. What we're going to do in this lecture is try to outline some ideas which make that intuition as rigorous as we can. And so a lot of that is going to be packaged in the idea of upper and lower bounds. So first of all, let's talk about upper bounds. A number m is called an upper bound of a if x is less than or equal to m for all x in a. All right. We can also say that a is bounded above in this case. All right. Now, likewise, if we have a number L such that L is less than or equal to x for all x in a, then a is said to have a lower bound, and you could also say that a is bounded below by L. And finally, if a subset A is both bounded above and below, then we just simply say that A is bounded. All right. Okay, so a simple proof, rather simple proposition we can state about these sorts of things is as follows. Let's see here. What's the proposition? A subset of R is bounded if and only if there exists m positive constant such that the absolute value of x is less than m for all x in the set A. So this is a biconditional proof. So I'll start with supposing it's bounded. So if it's bounded, that means that you can find an L1 and an L2 above and below every element in the set. I'm going to let L be the maximum of the absolute value of L1 and L2. And notice then that if m is equal to that, well, I also have that minus the absolute value of L1 is less than L1, and I have that the absolute value of L2 is larger than L2 itself, right? This is how absolute value works. And so that gives us that minus m is less than or equal to x is less than or equal to m, which tells us, among other things, that m is greater than or equal to L1. Well, I'm sorry, I'm explaining why this implies that. The reason this implies that is because we know that m is greater than or equal to L1 because we defined it to be the max of that. And we know that minus m is less than or equal to L1 because this implies that. And we also know that L2, the absolute value of L2 is less than or equal to m because, again, m is the max of the absolute value of L1 and L2. All right, so in any event, we have minus m less than or equal to x less than or equal to m, so that shows that this set is bounded both above and below by m, actually. But anyway, that's what we wanted to set out to prove, that there exists a positive constant such that the absolute value of x is less than that positive constant for every point in the set, and there it is. Now, conversely, if there exists an m such that the absolute value of x is less than or equal to that positive constant for all points in the set, then because of the rules we talked about in absolute value, we know that unwraps to minus m less than or equal to x less than or equal to m for all x in A, and so we find that it's bounded below. The set is bounded below by minus m, and it's bounded above by plus m. So consequently, the set is bounded, and that finishes the converse direction. So here's a picture of how m is chosen. If L1 and L2 happen to look like this, and the red picture is the set A, then the absolute value of L2 is going to be the largest thing if we look at the set absolute value of L1 and absolute value of L2. So it would pick absolute value of L2 as being the m, and minus m would be over there. So this proof it's a little bit greedy, right? Certainly minus m is not necessarily going to be the greatest lower bound, and you can think of other examples where m so constructed was not the least upper bound either. Oh, wait a minute. Greatest lower bound, least upper bound. What am I talking about? Well, glad you asked. That's what we're talking about next. But actually, first, I should remember to just, there's a trick I did in that previous proof, which was to introduce a maximum And the key thing about using a maximum is that it gives you inequalities with respect to the things you're taking the max of. Like if I take the maximum of alpha and beta, it's certainly less than or equal to alpha, and it's certainly less than or equal to beta. And so I used this general trick in the context of absolute value of L1 and absolute value of L2 in the previous little proof. I thought I should just make a standalone remark there. This is something we like to do. There's very similar things you could say about like minimum, right? Like the you could write good grief, what's wrong with me? Oh, I've already written it. I'm sorry, I'm just not seeing it. My eyes are not working. So here's how it works for max, here's how it works for min, right? The minimum is smaller than either of the inputs. The maximum is larger than either of the inputs. All right. Okay. Moving along here. So if I'm going to just move that up just a bit. Try to get to our next definition here. A non-empty subset of the reals, and suppose A is up to bounded above. We call the number alpha a least upper bound, or supremum of A, if, first of all, alpha is an upper bound, so x is less than or equal to alpha for all x in the set. And if m is an upper bound of A, then alpha is less than or equal to m. In other words, alpha is the least upper bound. And it can be shown that such an alpha, if it exists, is unique. And so we're going to denote alpha by the supremum of A, or some other text would use least upper bound or lub of A. So let me just go through the proof that it's unique if it exists. It doesn't take much. Here it is. Proposition: if A is a subset of the reals is non-empty subset with suprema alpha 1 and alpha 2, then alpha 1 equal to alpha 2. All right. Since alpha 1 and alpha 2 are both suprema, or supremums, both alpha 1 and alpha 2 are upper bounds, right, for A, but they're also least upper bounds, which means alpha 1 excuse me, is less than or equal to alpha 2, and alpha 2 is less than or equal to alpha 1, so it follows that alpha 1 equals to alpha 2. And there you have it. There's the uniqueness. It's basically following from point 2 here in the definition, essentially. And you can compare them one against the other or the other against the one, and so you get both inequalities, which gives you equality. Now, next up, of course, having defined the supremum, we can also define the infimum. And the infimum, or greatest lower bound, is defined very similarly. If you have a non-empty set and you have something that's a lower bound, and if you have the any other lower bound is smaller than that lower bound, then beta is said to be the greatest lower bound. And in the case it exists, we write that the infimum of A is equal to beta, which, as I mentioned, some other text would say GLB, greatest lower bound of A. And the proof that the greater lowest bound is unique, if it exists, is similar to the one that I just gave for the supremum, right? It shouldn't be. You should be able to do that, actually. It's not a bad thing. All right, so let's look at some examples. I want to calculate some suprema, some infima, and try to show you how we argue these things carefully. But I also want to show you a little bit about how to think about them intuitively, so we'll try to do both. So here we go. The supremum of -1 to 2 is equal to 2. So notice that 2 is not in the set. Whenever that's the case, it makes it a little tricky, but here's how it goes. If x is an element of -1 to 2, that means -1 less than or equal to x less than or equal to 2. Therefore, 2 is an upper bound for the set. All right? Now, suppose m bar less than 2 is an upper bound for -1 to 2. We're proceeding essentially by contradiction here. We want to show that there is no such thing as an upper bound smaller than m bar, smaller than 2. All right, so here we go. So what I'm going to do is I'm going to construct x naught as the midpoint of m bar and 2. Here's a picture of my thinking. So we're arguing 2 is in fact we want to prove that 2 is the least upper bound. So we're supposing towards a contradiction we've got a smaller upper bound, m bar. And the intuition is just that, well, the reason that this is going to fail is because in fact there are points between 2 and m bar, right? Like, for example, an easy point to find would be the midpoint, right? So now, for more complicated sets, you might have to worry that the midpoint wasn't actually in the set, but fortunately this is an interval from -1 to 2, so we'll be able to prove that x naught is actually in the set here, and that's what I'm setting out to do. This picture is an intuition, an intuitive guide, but it doesn't constitute a proof, all right? But anyway, so x naught is m bar plus 2 over 2. That gives me this as the midpoint. Great. So first of all, I would point out that m bar less than or equal to -1 provides a contradiction, as m bar is an upper bound on -1 to 2, right? It certainly can't be smaller than one of the elements in the set. That would contradict its its identity as an upper bound, right? So we can rightly assume that -1 is larger than m bar, right? So in other words, my picture is legit. Now, okay, so -1 less than m bar, and that implies that -1/2 is less than m bar over 2, which implies that 1/2 less than or equal to m bar over 2 plus 1. I added 1 across the inequality. And the reason I did these steps is because I wanted to get back to x naught again. So I got 1/2 is less than x naught. And so, of course, that also implies that -1 is less than x naught, right? Because certainly -1 is less than 1/2. Now, at this point, you might wonder, why didn't you leave it 1/2 less than x naught? That's more information. Okay, fine. Well, let's continue on. I'll explain why in a second. Okay, so m bar is also less than 2 by assumption, which means m bar over 2 is less than 1, which means that m bar over 2 plus 1 is less than 2. So we have that x naught is less than 2. So check that out. We've got x naught is greater than 1, or possibly equal to it, -1 rather, and we have that x naught is less than 2, which tells us what? It tells us that x naught is in here, right? In other words, x naught is an element of -1 to 2. But we can also show that x naught is greater than m bar, since the following. So let me give you the argument. All right. Notice that m bar is m bar over 2 plus m bar over 2, which is less than 1, because remember we have that m bar over 2 is less than 1, so I can replace one of these m bars over 2 with 1, and so that gives me that, but that's exactly x naught. So what that shows then, proof positive, x naught is greater than m bar. But we've also shown that x sub naught is an element of the set, and that's trouble because we've just shown that m bar is smaller than an element in the set, which means that m bar is not an upper bound, which is a clear contradiction. So what's that mean? That means that no such m bar exists, and we can conclude that m equals to 2 is in fact the least upper bound. That is, the supremum of -1 to 2 is equal to 2. Let's see here. So, just to drive that point home just a second here, we've done a proof by contradiction, right? And so we assumed that m bar was less than 2, and we made arguments, we reached a contradiction, right? So thus m bar is not less than 2, right? If m bar is not less than 2, that means that what? That means that m bar is greater than or equal to 2. And that's exactly what we need for 2 to be the supremum. We need that any other upper bound is larger than or equal to 2. That's why this contradiction proof proves what we want it to, okay? Let's go on to page 4, which is my example 2. My examples are pretty close to the examples in the text. We're in section let's see here, 1.5, yep. So we keep going here. Let me find my cover sheet. I don't want to overwhelm you with all these exciting inequalities all at once. Okay, so let me see where we are. All right, great. So I'm claiming that the infimum of -1 to 2 is equal to -1. All right, now this one's going to be easier because this time the the alleged greatest lower bound is in fact a point in the set in question. That makes the argument much easier, as we'll see. So certainly if x is in the interval from -1 included to 2 excluded, then -1 less than or equal to x less than 2. Therefore, L equals to -1 is a lower bound for the set. But suppose that L was another lower bound, all right, for -1 to 2. Then, since -1 is an element of -1 to 2, we find that L is less than or equal to -1, which is equal to the big L in my language, which shows you then exactly what we need to be true for -1 is the case, right? Any other lower bound is lower, so -1 is the greatest lower bound, and so we have shown that the infimum of -1 to 2 is equal to -1. That was so much easier than example 1 because we didn't have to fuss with that midpoint or any of that kind of trickier stuff, right? Because, again, it's because -1 was actually in the set we were allowed to make this little argument. So, just a remark, of course, when the supremum or the infimum is an element of the set, the argument is easier. All right, here's another one which will be easier. Supremum of 2, 4, 6, 8 is equal to 8. So clearly, if x is an element of 2, 4, 6, 8, then x is less than or equal to 8. Therefore, 8 is a upper bound. And if m is any upper bound, then 8 is less than or equal to m. So let's see here. Right, because 8 has to be lower than the upper bound, but that is exactly what we need to show that 8 is the greatest, well, excuse me, the least upper bound. Okay. All right. Now this example, I kind of stopped in my tracks when I was reading the notes, reading the book. The book is not, it's not wrong, but I feel like the book on this example is missing some detail, which I'd like to see from students in this kind of class. So, to be fair, I thought I should add the kind of detail that I'm looking for here. Although, well, it kind of depends on the instructions. If I say prove that the supremum of this is equal to 4, then I mean give an argument like I'm about to show you. If I say find the supremum of x squared such that -2 less than x less than 1, then I just want you to figure out that it's 4 and maybe draw me a picture or something to justify it, you know? Okay, so anyway, let A be the set in question, namely x squared from where x is ranging from -2 to 1, not included. I'm going to let y equal to x squared for the sake of conversation. Notice that x squared is equal to the absolute value of x squared. That's a fun little trick right there. And of course, if we have the absolute value of x squared is less than 4, right, which is, by the way, clear from this right here, right, because -2 is less than x less than 1, 1 is less than 2, so, you know, well, I guess I'm just saying, down here I'm just saying when absolute value of x is less than 2, it follows that, you know, absolute value of x squared is less than 4. Beware of the word when. When you see when in an English proof sentence, it's like rewriting an if-then as like a then this happens if that was true kind of sentence, which is, if you're not watching out for it, it can be tricky, right? I mean, basically what I'm saying is if this is true, then that follows, all right? And certainly that is the case when we're in the context of -2 less than x less than 1, because 1 is less than 2, which means minus 2 is less than x less than 2, which means the absolute value of x is less than 2. And so we have y equals x squared equals absolute value of x squared is less than 4 for all y in A. All right. Therefore, 4 serves as an upper bound for A, and we can say that A is bounded above by 4. Great. So, but is 4 the least upper bound? Well, let's see why. All right, suppose m less than 4 is an upper bound for A, so we're again proceeding by contradiction. We want to show that this blows up in our face, that in fact m less than 4 does not serve as an upper bound, and so by contradiction we get that m is greater than or equal to 4, which would then show that 4 is the least upper bound, which is what we want. So, all right, here's a picture. So I consider x bar equal to this minus the square root of m plus 4 over 2. So let me try to explain to you what's going on here. Here's the picture. So we've got this m less than 4 in the green. 4 is the honest to goodness greatest, least upper bound rather. And so I think of y bar as being the average of the 4 and the m. In other words, it's the midpoint on the y-axis between the green and the black dotted line. Now, and then what I want is I want this point of intersection right here. That's going to be the troublemaker. That when I square this guy, that's the troublemaker, right? So x bar is that x, right? My picture's not quite helpful, but that should be, it should be within, hey, let me call you back, okay? So, forgive me if I don't edit that out. It sometimes creates a corruption in the video file, and hopefully you won't be too offended by that. All right, so let's see here. So this picture is not quite right. Like that minus 2 should be like right under that. So that's on my artistry is like lacking. So this is supposed to line up with that, and so like this would be like x bar. Sorry. Okay, so x bar is minus the square root of m plus 4 over 2. And doing that will make the square of x bar be the average of the 4 and the m, which will lead us to the contradiction we're hoping for. All right, so let's stick with me here. It's going to take a little bit. We'll get to it. Okay, so 0 less than m less than 4 is true because m is a positive. M is assumed to be words. Let me say it this way. It should be clear that m has to be greater than 0, because if you put m less than or equal to 0, you can get a contradiction. So I guess my proof may be missing that, or maybe maybe it's here and I just haven't read it. But I guess technically I should establish that 0 has to be less than m. That's not immediately obvious. Let me just say, I'll just claim it. Okay, m less than or equal to 0 gives contradiction. It gives a contradiction since, 0 is an element of the set. All right. Just like in the previous argument, minus 1 being in the set helped us out. All right. I'm going to go on. Sorry, what I was trying to say is what I'm quibbling over right now would be analogous to this back in page 3. I said m bar less than or equal to minus 1 provides a contradiction because minus 1 is in the set. You can't have something in the set be larger than the upper bound. So we can justly assume that the upper bound is at least minus 1. All right. Okay, anyway, moving along. 0 less than m less than 4. And then I add 4 across this inequality, get 4 less than m plus 4 less than 8. Then I divide by 2, which gives me 2 less than m plus 4 less than 4. And then I take the square root of these positive set of inequalities. So I get square root of 2 less than or equal to square root, less than rather, the square root of m plus 4 over 2 less than the square root of 4, which is 2. And then I multiply the inequality by a minus 1. Notice that the first shall be last and the last shall be first. This 2 goes to minus 2, this root 2 goes to minus root 2. And so I flipped the inequalities and just rewrote them in that way. But that is what we need to see that x bar, which is this, is an element of the interval from minus 2 to 1. So consequently, the square of x bar, which we say is equal to y, is an element of A. Alright, so in other words, my picture is not just, my picture is reasonable. In fact, that stuff works out. Now let's see where the contradiction comes in. Yeah, x bar squared is m plus 4 over 2, which is m over 2 plus 2, right? And m is less than 4, which means that m over 2 is less than 2. Thus, x bar squared, which is m over 2 plus 2, is less than m over 2 plus 2, which is equal to m, which is to say that y bar equals x bar squared is greater than m. We have a point in the set is larger than the upper bound. That contradicts m being an upper bound. Therefore, m is not less than 4, in fact, which means m is greater than or equal to 4, which means that the supremum of A we can rightly conclude as being 4. So these details that I just went through for you here, these details are not quite in the text, and so what the text has is a sketch of the proof there, I think, not really the detailed proof that we'd like to see. All right. Proposition 1.5.1 gives us a kind of convenient technology, if you will, a way to calculate suprema and understand them using a little real parameter, a positive real parameter, which we typically denote by epsilon in the analysis course, right? You can almost always imagine epsilon as being a small positive parameter. And so that's the idea here, that A be a non-empty subset of the reals, the A be bounded above, then A is equal to, alpha is rather equal to the supremum of A, if and only if alpha is an upper bound, in other words, x is less than or equal to alpha for all x in A, and 2 prime, for any epsilon greater than 0, there exists some A in A such that alpha minus epsilon is less than A. So kind of here's the picture. If I take alpha and I go a little bit below it, whatever that is, alpha minus epsilon, then I can find an A between alpha and alpha minus epsilon, for which alpha minus epsilon is less than A, like in the picture. And the proof of this is actually quite simple. So here's the proof. So suppose, we'll go forward direction of the proof. Suppose alpha is its supremum, then alpha is an upper bound on A, so that means that 1 prime holds. Let epsilon be positive, and note that alpha minus epsilon is less than alpha, right? That's immediate because epsilon's positive. And thus alpha minus epsilon is not an upper bound of A. Therefore, that means that there exists an A for which alpha minus epsilon is less than A, right? And so thus 2 prime holds, because if alpha minus epsilon is less than A, well, that's the A for which that's exactly the A that we needed to establish 2 prime. Now the converse direction of the proof, here we go. Suppose that x is less than or equal to alpha for all x in A, and suppose that for any epsilon greater than 0, there exists A in A, such that A minus epsilon is less than A. In other words, we're assuming that conditions 1 prime and 2 prime hold. We'd like to argue that that is sufficient data to prove that alpha is the supremum. So, first of all, we've already got that alpha is an upper bound, so that's done. We just need to show it's the least upper bound. So let m be another upper bound less than alpha, right? We're working towards a contradiction here as usual. Let m less than alpha be an upper bound for A. And let epsilon equal to alpha minus m, right? That's going to be positive because we assume that m less than alpha. And hence, epsilon being positive, there exists an A in A such that A is greater than alpha minus epsilon, which is equal to m, again, because we're assuming that property 2' holds at the moment. That is to say that m is less than a for some a, but m is an upper bound, which is a contradiction. Woohoo! Thus, m is not less than or equal to alpha, and so m is greater than or equal to alpha, which shows that alpha is in fact the supremum of a as desired. So this proposition 1.51 is at times super convenient, especially for some examples. We'll see it eventually, I'm sure. 1.52 is the same song and dance except for infimum. For the infimum, the picture goes like this. The greatest lower bound is beta. You take beta plus epsilon. Well, there's got to be some point in the set that's between these two guys, if beta is in fact as advertised and is the infimum. So if beta is equal to the infimum, if and only if beta is a lower bound, right, that's 1', and then for any epsilon greater than 0, there exists an a in the set such that a is less than beta plus epsilon. So the proof of proposition 1.52 is very similar to proposition 1.51, and I will omit it. Finally, that brings us to the most important statement for today, which is the completeness axiom. Every non-empty subset A of the reals that is bounded above has a least upper bound. That is, the supremum of A exists and is a real number. So this is an axiom, which means it's not something I can prove for the real number system. But that said, you can show that this feature holds for a particular construction of the real numbers. Like if I was to build the construct the real numbers from limit points of Cauchy sequences, or if I was to build the real numbers from Dedekind cuts, we could show that the completeness axiom holds for those constructions. But insofar as defining the real numbers is concerned, where we're just trying to define real numbers by its properties kind of philosophy here, this is basic. This is a fundamental fact about real numbers that we're going to work with the completeness axiom. So let me show you a set of numbers which is like the real numbers but doesn't have this. The rational numbers, right? So the rational numbers, we could look at the set x such that x is like a truncated decimal representation of 2 out to n digits. So like truncating at the first digit, we got 1. Truncating, chopping off the, I don't know, it's debatable. Truncated at, I don't know if I should put 1 in there. Truncated at n digits. If you truncate 1 digit, I mean decimal digits, all right? I don't know how to say that. Decimal places. Let's say places. I like that better. And decimal places, right? Like cut off 1 decimal place, you just left with 1, right? If you cut out at the second decimal place, you got 1.4. Then you got 1.414. The point is, if you look at any one of these, they're rational, right? They're a ratio of like 14 over 10 or 1,414 over 1,000, and so forth and so on. These are all rational numbers. It's a subset of the rational numbers. It's bounded above by the square root of 2. And in fact, you can prove that the square root of 2 is the least upper bound for this guy, right? So the supremum of A is in fact equal to the square root of 2. But we will prove that the square root of 2 is not a rational number. So this shows you that the rational numbers form in fact, they do form an ordered field. And what this shows is that they are not complete, because here's a set which is bounded above, but the supremum of the set, the least upper bound, does not exist in the rational numbers. All right. So it's important that the supremum exists and is a real number. All right. That's what's needed there. Okay, so theorem. Suppose that A and B are non-empty subsets of the reals. A is a subset of B. If B is bounded above, then the supremum of A is less than or equal to the supremum of B. So here's the proof. If we suppose B is bounded above by beta, that means x is less than or equal to beta for all x in B. However, if x is in A, then x is in B because A is a subset of B, right? Therefore, thus I should say x is less than or equal to beta. for all x and a. That means that a is bounded above, and then by the completeness axiom, the supremum of a exists, right? But anyway, supremum of b is an upper bound for b, which means it's also an upper bound for a, right? Because a is inside b, so whatever works to be above elements of b is also above elements of a. And so by definition, 2 prime, since b is the so since supremum of b is an upper bound for a, and supremum of a is the the least upper bound, it follows that supremum of a is less than or equal to the supremum of b, essentially by definition of supremum. So it's there's a theorem that's kind of neat. There's a corresponding theorem for infimum. I think it's the last exercise in this section. So finally, just to end this story here, we can introduce infinity and minus infinity as formal symbols and talk about the extended real number system. You can give it an ordering, which is kind of heavy-handed. Minus infinity is less than everything. Infinity is greater than everything, real-wise, right? And anything plus infinity is infinity. Anything minus infinity is minus infinity. Take positive number times infinity, it's infinity. Take a negative number, positive number times minus infinity, it's minus infinity. If you multiply by a negative number, it flips infinity to minus infinity, and minus infinity to infinity. The sum of infinity with itself is infinity. The sum of minus infinity with itself is minus infinity. The product of plus or minus infinity with plus or minus infinity is infinity. And likewise, if we multiply infinities of differing signs rather, we get minus infinity. So these, what I've written here, I would say these are all the patterns that I teach Calculus 1 students, as these are not indeterminate forms, these are just forms that blow up, right? Like, if you can get your limit down to one of these patterns, like, it's not debatable anymore, it's just, game over, it blows up, right? In contrast, of course, in Calculus 1, we look at also the indeterminate forms, 0 times infinity, infinity plus minus infinity plus infinity. These, when we have limits that follow these patterns, we don't know for certain what it's going to work out to. It could work out to a lot of different things, depending on how the algebra works out, right? So similarly here, we do not try to define those indeterminate forms. We just, what's in the green is what it is. And subject to those terms and conditions, we can talk about the extended real number system. Not a field, like the algebra is a little limited in what you can do there, but it is enough to at least allow us to say that if A is a non-empty subset and it's not bounded above, then we can define the supremum to be infinity. And if you have a non-empty subset not bounded below, you can define the infimum to be minus infinity. And with that convention, you get to say that non-empty subset of the reals has a supremum and infimum in the extended reals. And if you're further inclined, you can define the supremum of the empty set to be minus infinity and the infimum of the empty set to be infinity, which kind of like, I was like, what? I wanted it to be the opposite, but I'm wrong, and the reason I'm wrong is simple enough. If you think about empty set being a subset of A, you'd like that the supremum of the empty set is less than the supremum of A, just to make that theorem that we looked at on page 7 hold true. And so if you make the supremum of the empty set to be minus infinity, it's going to work. And vice versa, if the infimum of the empty set is going to be greater than the infimum of A, you want to choose the infimum of the empty set to be infinity, so it works. So basically, this definition for the supremum and infimum of the empty set ensures that the theorem, or the proposition, what was its number? Theorem 1.5.3 on page 25 of the text here holds for like arbitrary sets. So anyway, that's it for now. Next time we will be talking about section 1.6, which I think is on applications of the completeness axiom, and I think you might find that more interesting. I don't know. Anyway, thanks for listening, and talk to you guys later.